Hello, everybody. I'd like to talk to you for a few minutes about limits and continuity. And I'm going to introduce you to some definitions that will help clarify. So, what is continuity? Definition. Continuity at a point. Assume that f of x is defined on an open interval. Containing x equals c. Then f is continuous at x equals c if the following occurs. The lim as x approaches c of f of x equals f of c. And here's what it looks like. So here's a graph. And I have a curve here, which, let's see, so there's the curve, and the point in question will be right here. Okay. So this is C. This is A. This is B. It's an open interval. C is within an interval. The limit is defined from the left and the right. And since it's defined from the left and the right, this part checks out right. The left side of this equation. This piece here checks out okay. And it is defined, and that part is true. Now, we also have some other types of continuity. For example, we have one-sided continuity. So we have one-sided continuity. So to start with, we'll look at left continuous. How would we define left continuity? We're going to write the lim as x approaches c from the left of this function equals f of c. So let's write this down. So here is left continuity. That's left continuous. And you can see where it's defined from the left side. And this is C. So we have left, and then we also have right continuous. And right continuous is defined as lim as x approaches C from the right of this function equals f of C. Removable discontinuity. So here's an example of removable. I'm going to put a curve here with an open dot. And then right above it, I'll put a solid dot. And all this occurs at C. So I'll give you a second to write that down. Now we have three conditions. One, the lim as x approaches C of f of x exists. 2, f of C exists. And 3, they are equal. So, does the limit of f of x as x approaches C exist? So my question, a question we want to ask ourselves, does a function have to be defined at a point to have a limit? Or another way of saying it is, if a function is not defined, does a limit exist? And from our definition of limit, all we are trying to do is approach the value. So whether the function is defined or not, it has nothing to do whether there is a limit, because all we're trying to do is to approach the limit. So if you, for number one, for the limit of the function as x approaches C, does it exist? And the answer is yes, it exists, because it's not required to be defined there. So this is true. Does f of C exist? Yeah, it does exist. It exists right here at the solid dot. Are they equal? No. So when you answer these three questions like this, if you come out with true, true, and a false, you know that you have a removable discontinuity. So let me explain this one more time. Just because a function is not defined at a point does not disqualify it from having a limit. Because by definition of the limit, all we're trying to do is approach the value. And that can occur if it's defined or not defined. We still have a limit. Now, going back to our previous example, picture, I'm going to draw a curve that looks like this. Now, what type of discontinuity exists here? This is what's known as a jump discontinuity. It's a jump discontinuity, but remember, we already said it was left continuous. Okay? Now, let's look at a function let me change some of the colors around here. So this is 1, 1, 2, that's 3. This is 1, 2, 3. And it ends at 5. Now, I can write this function. I drew the picture, and here's how the function is defined. We use what's called a piecewise function notation. And the condition for that is x is less than 1. 3, 4, is less than or equal to 3, and x for x is greater than 3. All right. So this is f of x. This whole blue configuration. Now, here are the questions. The lim as x approaches 1 from the left of f of x. Now, you want to go back to the original piecewise function and you want to look at it. You know that the limiting value is the value that cannot be obtained. So that's what we're looking for. And we want to know, well, what is the limit as we approach 1 from the left? So if I approach 1 from the left, I'm going this way. And I'm going to stop when I get to 1. So I'm approaching this 1, and I ask myself, when x is 1, what is y? And look at the endpoint right there. What is the y value for that? Well, if you go over this way, you'll see that it is 1. So we write 1. Okay? Now, what is the limit as you approach 1 from the right of this function? Now, 1 from the right, well, look right here. There's nothing around in this area right here. So that area is out. The part that you want to make sure that you're looking at is this piece up here. Okay, so you're going to jump up, and it says 1 from the right. From the right. So 1 from the right means start right, go left. And what is the y value there? So you're saying when x is 1, what is y? It is 3. And the last one, the limb as x approaches 1 from the left and the right. Well, look at what it was from the left. It was 1. And from the right, it was 3. So we would say it does not exist. And why? We would say it does not exist since the limb as you approach 1 from the left does not equal the limb as you approach 1 from the right. Move this over a little bit for you. We would say since the following: the limb as you approach 1 from the left of the function does not equal the limb as you approach 1 from the right of that same function. Now, we also have something called infinite discontinuity. And it looks something like this. Infinite discontinuities have asymptotes in them. So here it is. There's the asymptote. Continue this way. That's one example. You also have an example like this, where we'll have an asymptote But the function goes down like this, and the other part goes like that. Okay? So those are infinite discontinuities. All right, so in my next video, I'm going to go over how to evaluate some functions and what you are exactly we're looking for.